I want to thank all of you for coming to GTC. We talked about several things. One, Blackwell is in full production. We essentially wanted to build this chip. It's just that no reticle limits can do this. No process technology can do this. It's 130 trillion transistors. 20 trillion of it is used for computing. So it's not like you can't reasonably build this anytime soon. And so the way to solve this problem is to disaggregate it, as I've described, into the Grace Blackwell NVLink 72 rack. But as a result, we have done the ultimate scale-up. This is the most extreme scale-up the world has ever done. The amount of computation that's possible here, the memory bandwidth, 570 terabytes per second. Everything in this machine is now in T's. Everything's a trillion. And you have an exaflops, which is 1,000,000 trillion floating point operations per second. Well, the reason why we wanted to do this is to solve an extreme problem. There's an inflection point in AI. The amount of computation we have to do in AI is so much greater as a result of reasoning AI and the training of reasoning AI systems and agentic systems. Second, Blackwell NVLink 72 with Dynamo is 40 times the performance, AI factory performance of Hopper. And inference is going to be one of the most important workloads in the next decade as we scale out AI. It is essentially the operating system of an AI factory. Whereas in the past, in the way that we ran data centers, our operating system would be something like VMware. And we would orchestrate, and we still do, we're a big user, we orchestrate a whole bunch of different enterprise applications running on top of our enterprise IT. But in the future, the application is not enterprise IT, it's agents. And the operating system is not something like VMware, it's something like Dynamo. And this operating system is running on top of not a data center, but on top of an AI factory. Third, we have an annual rhythm of roadmaps that has been laid out for you so that you could plan your AI infrastructure. We plan this out in multiple years. The next click, 1 year out, and Rubin, brand new GPU, CX9, brand new networking smart NIC, NVLink 6, brand new NVLink, brand new memories, HBM4. Basically, everything is brand new except for the chassis. And this way, we could take a whole lot of risk in one direction and not risk a whole bunch of other things related to the infrastructure. And so Vera Rubin, NVLink 144, is the second half of next year. This now sets the stage for the second half of the year, the following year, we call Rubin Ultra. It's NVLink 576, extreme scale up. Each rack is 600 kilowatts, 2.5 million parts, okay? And obviously a whole lot of GPUs. And everything is X factored more. So 14 times more flops, 15 exaflops. Instead of one exaflop, as I mentioned earlier, is now 15 exaflops, scaled up exaflops, okay? And it's 4.6 petabytes, so 4,600 terabytes per second scale up bandwidth. I don't mean aggregate, I mean scale up bandwidth. And of course, a brand new NVLink switch and CX9. Now that gives you a sense of the pace at which we're moving. This is the amount of scale-up flops. This is scale-up flops. Hopper is 1x, Blackwell is 68x, Rubin is 900x. We have 3 AI infrastructures we're building. AI infrastructure for the cloud, where the data centers are now the size of the stadium. We're going to need something much long distance running. And that's just where silicon photonics comes in. The challenge of silicon photonics has been that the transceivers consume a lot of energy. To go from electrical to photonic has to go through a SerDes, go through a transceiver and a SerDes, several SerDes. This is 30 watts, just so keep you remember, this is 30 watts. And if you buy it in high volume, it's $1,000. This is the amazing thing that we did. We invented the world's first MRM micromirror, and this is what it looks like. There's a little waveguide. You see that on that waveguide goes to a ring. That ring resonates, and it controls the amount of reflectivity of the waveguide as it goes around, and limits and modulates the energy, the amount of light that goes through. And it shuts it off by absorbing it or pass it on. Okay, it turns the light, this direct continuous laser beam, into ones and zeros. And that's the miracle. In order for us to take AI to enterprise, take a step back for a second and remind yourself this. Remember, AI and machine learning has reinvented the entire computing stack. The processor is different, the operating system is different, the applications on top are different. The way the applications are different, the way you orchestrate it are different, and the way you run them are different. Let me give you one example. The way you access data will be fundamentally different than the past. Instead of retrieving precisely the data that you want and you read it to try to understand it, in the future, we will do what we do with Perplexity. Instead of doing retrieval that way, I'll just ask Perplexity what I want. Ask it a question, and it will tell you the answer. This is the way enterprise IT will work in the future as well. We will also revolutionize the rest of the computing stack. Remember, computing has 3 pillars. There's computing, you're looking at it. There's networking, as I mentioned earlier, Spectrum-X going to the world's enterprise, an AI network. And then third is storage. Storage has to be completely reinvented. Rather than a retrieval-based storage system, it's going to be a semantics-based retrieval system, a semantics-based storage system. And so the storage system has to be continuously embedding information in the background, taking raw data, embedding it into knowledge, and then later when you access it, you don't retrieve it, you just talk to it. You ask it questions, you give it problems. The time has come for robots. Robots have the benefit of being able to interact with the physical world and do things that otherwise digital information cannot. We know very clearly that the world has severe shortage of human laborers, human workers. By the end of this decade, the world is going to be at least 50 million workers short. We'd be more than delighted to pay them each $50,000 to come to work. We're probably going to have to pay robots $50,000 a year to come to work. And so this is going to be a very, very large industry. Today I'm going to show you 2 things. One of them is so that we could scale AI with generative capabilities. A generative model that understands the physical world. We call it Cosmos. Using Omniverse to condition Cosmos, and using Cosmos to generate an infinite number of environments allows us to create data that is grounded, controlled by us, and yet be systematically infinite at the same time. And so today we're announcing something really, really special. It is a partnership of 3 companies, DeepMind, Disney Research, and NVIDIA, and we call it Newton. Thank you. All right, let's start that over, shall we? Let's not ruin it for them. Hang on a second. Somebody talk to me. I need feedback. What happened? I just need a human to talk to. Janine, I know it's not your fault, but talk to me. We just got 2 minutes left.
I'm right here. They're re-racking it.
They're re-racking it? I don't even know what that means. Okay. Can you imagine just now what you were looking at is complete real-time simulation? This is how we're going to train robots in the future. Just so you know, Blue has 2 computers. 2 NVIDIA computers inside. Look how smart you are. Hey, Blue. Let's go home. Good job. Good little man.